When you talk to one of these AI systems, it has no memory of you. Not in the way you would recognize as memory. Everything it appears to know about the current conversation, it is holding in its hands all at once, the way you might hold every card in a game face up in front of you, and the moment the conversation ends, it puts them all down and forgets your face entirely. The size of that handful has a name, and that name is quietly the most important number in the feed right now. Now, I should say where I stand, because this video is going to end with an opinion. I think the race that everyone is watching, the race for the cleverest model, is not actually the interesting race. The interesting one is the race to let a model hold more in mind at once without the cost exploding. And a model released this month is the clearest illustration yet of why that race is so hard and what it takes to win a lap of it. Because that handful of cards has been, until very recently, painfully small. The amount a model can consider at one time is called its context window, and for years it was a few pages of text. You could give it a chapter. You could not give it the book. And everything people found frustrating, the forgetting, the losing of the thread, was really that small window quietly running out of room. And if you asked most people why the window was small, they would probably guess memory, in the sense of storage, as though the machine simply ran out of shelf space. But you know what? That is not the reason. The reason is that the standard way these models read has a cost that grows in a particularly vicious shape, and it is worth seeing exactly why, because everything else follows from it. So here is what we are going to do. First, why reading more has cost so much more, not a little more. Then, the two ideas the newest models are using to bend that cost down. And finally, the big one. The specific machine released this month, the numbers attached to it, and whether bigger really is better here. First up, the vicious shape. The standard mechanism these models use is called attention, and the plain description of it is that, to understand each word, the model compares it against every other word in the window. That comparing everything to everything is what lets it grasp how a sentence hangs together. It is genuinely most of the magic, and it is also the problem. Because comparing everything to everything does not get twice as expensive when you double the text. It gets 4 times as expensive. 10 times the text is 100 times the work. This is what people mean when they say the cost grows with the square. And squares grow in a way human intuition consistently underestimates. Double and you quadruple. That single fact is why the window stayed small for so long. Let me make that concrete. A window of 1,000 words involves on the order of 1,000,000 comparisons. Push it to 1,000,000 words, the thing everyone now wants, and the naive arithmetic lands somewhere around 1,000,000,000,000. Same method, same model, just more text held in mind. The method does not scale. It was never going to be enough on its own. So that is the word. And the last couple of years of progress, the part that does not make headlines, has mostly been an argument about how to get around it. There are two broad moves, and the newest models tend to use both at once. The first move is to stop insisting that every word attend to every other word. Most words, honestly, do not need to consult the entire document to be understood. So you replace the compare everything step with something lighter, a scheme that grows in a gentler, more linear way, and you accept a little imprecision in exchange for a cost that no longer explodes. This family of ideas is usually called linear attention, and the trick is doing it without the model becoming noticeably stupider. The second move is about the model itself, rather than how it reads. Instead of one enormous network where every part activates for every single word, you build many specialized subnetworks, and for each word you switch on only the few that are relevant. The whole thing is huge, but the part actually working at any instant is small. This design has a name that sounds more complicated than it is: a mixture of experts. And this month gave us an unusually clean demonstration of all of it, from a Chinese lab called Moonshot in a model called Kimi K3. And the numbers are genuinely arresting, provided you read them the right way, which almost no coverage does. Start with the headline, 2.8 trillion. That is the total number of parameters, the internal dials, in the model, and it makes this one of the largest ever openly released. Read on its own, that number is close to meaningless, and it is the number everyone quotes. Here is the number that actually matters. Of many hundreds of expert subnetworks inside it, only 16 are switched on for any given word. So the model is enormous in what it knows, and comparatively modest in what it runs. The size lives in the warehouse, the cost lives on the counter. And keeping those two apart is the entire point of the design. And on top of that sits the number this whole video has been circling. A context window of 1 million tokens, which is very roughly a million words held in mind at once. Long enough to hand it an entire codebase or a shelf of documents and ask a question that depends on all of it. That is the handful of cards, made enormous without the square-shaped cost eating the whole machine alive. And the reason a lab can simply release something like this, weights and all, for anyone to run, is worth pausing on. A frontier that used to belong to a handful of American companies now very visibly does not. The most capable openly available model being this large and coming from Moonshot rather than from the usual names is a genuine shift, whatever one thinks of the wider competition. And honestly, this is where I want to push back on the framing, because the coverage of all this is a touch breathless. 2.8 trillion is not a score, nobody experiences a parameter. A larger window is not automatically a better answer. And there is by now good evidence that models grow inattentive in the middle of a very long context, technically present, but not really reading it, in the way you can run your eyes down a page and take in none of it. Capacity is not the same thing as comprehension, and the number that markets a model is rarely the number that measures it. Now, to be fair to the ambition, having the room is a genuine precondition. You cannot reason about a whole code base. You were never able to fit in the window in the first place. Expanding what a model can even take in is real progress, and the architectural work that made 1 million tokens affordable is not marketing, it is the hard part, done well. But I think the honest summary is that the field is quietly changing what it competes on. The bragging rights are still about size and cleverness, because those make clean headlines. The actual engineering, the part that decides what these systems can really do, has moved to a different question. Not how much a model knows, but how much it can hold in mind at once and at what price. That is a less glamorous contest, and it is the one that matters. So the next time one of these systems seems to understand a long and complicated thing you have handed it, remember what is actually happening. It is holding the whole of it in front of itself at once, briefly at real expense. And the only reason it can afford to is that a great deal of clever engineering has gone into making that handful of cards larger without making it ruinous. It still forgets your face the moment you leave. The achievement is only that, for a little while, it could hold so much of you at all.